I am Dr. L Madhuchelvi, Associate Professor of Mathematics, Sri Sharada College for Women, Salem. In this session, we will talk about trace and transpose of a linear transformation. Trace and transpose of a linear transformation. First, let us see what is called a linear transformation. A linear transformation is nothing but a vector space homomorphism. First, let us see the trace and transpose of matrices. The trace of a matrix A is sum of the elements on the main diagonal of A. If A equal to the matrix alpha ij, that is alpha 1 1, alpha 1 2, etc., alpha 1 n, alpha 2 1, alpha 2 2, etc., alpha 2 n, and so on, alpha m1, alpha m2, etc., alpha mn are the square matrix of dimension n by n. Then the trace of A is defined as the sum of the main diagonal of A, that is alpha 1 1 plus alpha 2 2, etc. If it is a square matrix of order n, then plus alpha n n. That is summation I equal to 1 to n alpha ii. Let us see the lemma, first lemma on the properties of trace. For A comma B belongs to Fn and lambda belongs to F, trace of lambda A equal to lambda into trace of A. Second one, trace of A plus B equal to trace of A plus trace of B. Third one, trace of AB equal to trace of BA. Let us see the proof. First one, to prove trace of lambda A equal to lambda into trace of A. What is trace of A? Trace of A equal to summation I equal to 1 to n alpha ii if A equal to the matrix alpha ij. Then trace of lambda A equal to summation I equal to 1 to n lambda into alpha ii. Let us take the scalar outside, then we can get lambda into summation I equal to 1 to n alpha ii, that is lambda into trace of A. Second property, we are going to prove trace of A plus B equal to trace of A plus trace of B. If A equal to alpha ij and B equal to beta ij, then A plus B equal to alpha ij plus beta ij. Then trace of A plus B equal to the sum of the diagonal elements of A and the matrix B. That is summation I equal to 1 to n alpha ii plus beta ii. So we can take that separately, that is equal to summation I equal to 1 to n alpha ii plus summation I equal to 1 to n beta ii. That is equal to trace of A plus trace of B. So trace of A plus B equal to trace of A plus trace of B. Then the last property, if A equal to alpha ij and B equal to beta ij, we are going to prove trace of AB equal to trace of BA. That is AB equal to, let us say the product of two matrices, that is equal to gamma ij, where gamma ij equal to summation k equal to 1 to n alpha ik into beta kg by using the matrix multiplication. Then BA, we can write BA equal to the matrix mu ij, where mu ij equal to summation k equal to 1 to n beta ik alpha kj. Then trace of AB equal to summation I equal to 1 to n, what is that? Gamma ii. That is equal to summation I equal to 1 to n, k equal to 1 to n, we have alpha ik, beta ki. If we interchange the order of the sum in the last one, we get trace of AB equal to summation k equal to 1 to n, summation I equal to 1 to n, alpha ik, beta ki. That is equal to summation k equal to 1 to n, summation I equal to 1 to n, beta ki, alpha ik. That is nothing but mu kk. So summation k equal to 1 to n mu kk, that is trace of BA. So trace of AB equal to trace of BA. So these are the three properties of the trace, that is trace of lambda A equal to lambda into trace of A, trace of A plus B equal to trace of A plus trace of B, trace of AB equal to trace of BA. Then we can move to the corollary of this lemma. If A is invertible, then trace of AC A inverse equal to trace of C. Proof, let B equal to C A inverse. Let us take B equal to C A inverse. Then trace of A C A inverse equal to trace of A into B. In place of C A inverse, we put B, trace of AB. So by the above lemma, what is trace of AB? Trace of AB equal to trace of BA. So trace of BA is trace of B is CA inverse into A. That is, A inverse A is the identity matrix. So C into I, that gives you C. So that is equal to trace of C. So if A is invertible, then we have trace of AC A inverse equal to trace of C. Next, we will see the definition. If T belongs to AFE, then what is the, now only we are going to define the trace of a linear transformation. If T belongs to AFE, then trace of T is the trace of M1 of T, where M1 of T is the matrix of T in some basis of V. Then we can see one remark. Trace of T depends on T and not on any particular basis of V. So if you have V, the vector space, it has more than one basis. Then trace of T depends on T only, the transformation only, and not on any particular basis of V. Let us see the proof. If M1 of T and M2 of T are the matrices of T in two different bases of V. By the known theorem, we have M1 of T and M2 of T are similar matrices. If it is so, M1 of T and M2 of T are similar matrices. By the above corollary, we have they have the same trace. So trace of T depends on linear transformation only and not on any particular basis of V. Then let us go to the lemma, 6.8 lemma. Next lemma, if T belongs to A of V, then trace of T is the sum of the characteristic roots of T using each characteristic root as often as its multiplicity. Let us go to the proof. We can assume that T has a matrix in Fn. Let K be the splitting field for the minimal polynomial of T over F. Then in Kn, by the known theorem, M of T can be brought to its Jordan form, J. J is a matrix on whose diagonal appear the characteristic roots of T. The characteristic roots of T appears on the diagonal. That is diagonal of J. What is J? J is the Jordan form of M of T. Then each root appearing as often as its multiplicity. So trace of J is the sum of the characteristic roots of T. Since J is of the form A, M of T, A inverse, trace of J equal to trace of A, M of T, A inverse. Then by the known corollary, we have trace of AB equal to trace of BA. Using that, we can get trace of J equal to trace of MT. So it is the theorem, that is, it is the lemma. What is the lemma? If T belongs to AFE, then trace of T is the sum of the characteristic roots of T. Because we know that each characteristic, that is the characteristic roots appearing on the diagonal of a matrix of T. So it is the trace of T is the, we know that is the trace of m of t only. So in m of t, we are having its Jordan form, and the Jordan form can be written in the form A m of t A inverse. Then what is that? Using the above lemma, that is trace of C inverse equal to, that is by using the lemma, trace of A inverse equal to trace of C. Here we are getting trace of A m of t A inverse equal to trace of m of t. Then next, we can go to the another lemma. If f is a field of characteristic 0 and if t belongs to A of v over f is such that trace of t power I equal to 0 for all I greater than or equal to 1, then t is nilpotent. The lemma says if f is a field of characteristic 0 and if t belongs to A of v over f is such that trace of t power I equal to 0 for all I greater than or equal to 1, then t is nilpotent. Before that, we can recall the definition of nilpotent linear transformation. What is the called a nilpotent linear transformation? The definition: t is nilpotent if t power k equal to 0 for some positive integer k. So let us see the proof now. Let t belongs to A of v over f, and let p of x, that is the polynomial, it is of the form x power m plus alpha 1 x power m minus 1 plus an etc. plus alpha m be the minimal polynomial of t. So by the definition of the minimal polynomial of t, we get p of t equal to 0. That is t power m plus alpha 1, t power m minus 1 plus an etc. plus alpha m equal to 0. Taking trace both sides, we get trace of t power m plus alpha 1, t power m minus 1 plus an etc. alpha m equal to, that is trace of 0 linear transformation, that is equal to 0. So this can be written as trace of t power m, because we know that a trace of a plus b equal to trace a plus trace b. So trace of t power m plus trace of alpha 1 t power m minus 1 plus an etc. plus trace of alpha m. And also we know that trace of lambda a equal to lambda into trace of a. So using that here for a linear transformations, we can write trace of t power m plus alpha 1 trace of t power m minus 1 plus an etc. plus trace of alpha m equal to 0. Then, since we know that a trace of t power I equal to is given in the hypothesis, trace of t power I equal to 0 for I greater than or equal to 1, we get trace of alpha m equal to 0. So, if dimension of v equal to n, then trace of alpha m equal to alpha m into trace of I is the identity matrix of dimension of v, that is n. So, alpha m n. Therefore, n into alpha m equal to 0. Since the characteristic of f is 0, that is given in the hypothesis, so n not equal to 0, that implies alpha m equal to 0. So let us consider T as a matrix in Fn and also a matrix in Kn, where K is an extension of F, which contains all the characteristic roots of T. So we can bring T to a triangular form, and since 0 is the characteristic root of T, we can bring it to the form 0, 0, beta 2, alpha 2, etc. 0, beta n, etc. alpha n. That is, we can write as 0, 0, that matrix, that non-zero matrix, and T2, where T2 equal to alpha 2, 0, 0, etc. alpha n. T2 is n by n minus 1 by n minus 1 matrix. Now T power k equal to 0, 0, that non-zero matrix, and T2 power k. Since trace of T power k equal to 0, so we have trace of T2 power k also equal to 0. Thus, T2 is an n minus 1 by n minus 1 matrix with the property that trace of T2 power k equal to 0 for k greater than or equal to 1. Using the same argument as in the first paragraph of the proof for T2, the matrix of T2 can bring it to the form then 0, 0, gamma 3, alpha 3, etc. 0 in this form, that is 0, null matrix, 0, then non-zero matrix, and some T3, where T3 is alpha 3, 0, 0, etc. 0 alpha n. Then it is an n minus 2 by n minus 2 matrix. So T2 power k equal to 0, 0, then non-zero matrix, and then T3 power k. So trace of T2 power k equal to 0 plus trace of T3 power k. Since trace of T2 power k equal to 0, trace of T3 power k also equal to 0. Thus, T3 is an n minus 2 by n minus 2 matrix with the property that trace of T3 power k equal to 0. Continuing in this way, we get alpha 3 equal to alpha 4 equal to etc. alpha n equal to 0. Thus, T is brought to a triangular form. All its entries are the main diagonal or entries in the main diagonal are 0. Hence, T is nilpotent. So, we prove that the lemma, if F is a field of characteristic 0 and if T belongs to A of A is such that trace of T power I equal to 0 for all I greater than or equal to 1, then T is nilpotent. Then next, let us see the Jacobson lemma. If F is of characteristic 0 and if S and T in A of A are such that ST minus TS commutes with S, then ST minus TS is nilpotent. This lemma is known as Jacobson's lemma. What is it? If F is of characteristic 0 and if S and T in A of A over F are such that ST minus TS commutes with S, then we have to prove ST minus TS is nilpotent. Let us see the proof. For any k greater than or equal to 1, let us compute ST minus TS whole to the power k. That is, ST minus TS whole to the power k is, can be written as ST minus TS whole to the power k minus 1 into ST minus TS. That is equal to ST minus TS whole to the power k minus 1 into ST minus TS whole to the power k minus 1 into TS. Since ST minus TS commutes with S, the term ST minus TS whole to the power k minus 1 into ST can be written in the form S of ST minus TS whole to the power k minus 1 into T. Let B equal to, let us assume B equal to ST minus TS whole to the power k minus 1 into T. That is, ST minus TS whole to the power k can be written as SB minus BS. Hence, trace of ST minus TS whole to the power k equal to trace of SB minus BS. That is, trace of SB minus trace of BS. But we know that trace of AB equal to trace of BA. So, trace of SB minus trace of BS equal to 0. So, by trace of T power k equal to 0 implies T is nilpotent. By using that lemma, we can say here ST minus TS is nilpotent. Next, let us see one definition. If A equal to alpha ij belongs to Fn, then the transpose of A written as A dash equal to gamma ij, where gamma ij equal to alpha ji for each I and j. Then we can say one lemma, and for all A comma B belongs to Fn, A dash of dash equal to A, that is A transpose of A transpose equal to A plus B whole transpose equal to A transpose plus B transpose, and third one AB transpose equal to B transpose into A transpose. So let us say A transpose of transpose equal to A first. Let us consider A equal to alpha ij, then by the definition A transpose equal to gamma ij, where gamma ij equal to alpha ji. Then A transpose of transpose equal to alpha ij, where that alpha, because A transpose equal to alpha ji, so A transpose of transpose, by the definition we get alpha ij, that is equal to A. So A transpose of transpose equal to A. And then let us say A plus B transpose equal to A transpose plus B transpose. It is also the same way. A transpose equal to gamma ij and B transpose equal to delta ij. A is the matrix alpha ij and B is matrix beta ij. So A plus B equal to some mu ij. A plus B whole dash equal to, let us consider, that is equal to some gamma ij, where gamma ij equal to mu ji. Then A transpose equal to, let us consider here A transpose equal to delta ij, where delta ij equal to alpha ji. B transpose equal to Tij, where Tij equal to beta ji. Then A transpose plus B transpose equal to delta ij plus Tij, that is delta ij plus Tij, where delta ij plus Tij equal to alpha ji plus beta ji. That is equal to mu ij, since alpha ji plus beta ji equal to mu ij. So A dash plus B dash equal to gamma ij, since gamma ij equal to mu ji. Here we have mu ji only. Thus, A plus B whole dash equal to, that is transpose of A plus B equal to A transpose plus B transpose. In the same way, the last one, we can say the product. Let A transpose equal to delta ij and B transpose equal to Tij, where delta ij equal to alpha ji and Tij equal to beta ji. A, B equal to some mu ij, that is equal to summation k equal to 1 to n alpha ik beta kj by the using the definition of the matrix product. That is equal to alpha ij into beta ij, where mu ij equal to summation k equal to 1 to n alpha ik into beta kj. So AB dash equal to gamma ij, where gamma ij equal to mu ji, that is equal to summation k equal to 1 to n alpha jk beta ki. So B dash A dash equal to summation k equal to 1 to n tik delta kj, that can be written as beta ki alpha jk, and we have gamma ij, that is equal to AB whole dash. So transpose of AB equal to B transpose into A transpose. So we saw in this session that trace and transpose, definition of trace and definition of the transpose, and some properties of some lemmas on trace and transpose. Thank you.